I got started early. I'm just excited. Stuff to write on.
Hey, I'm done. If you could make that happen, I don't know.
Something to write ideas on. I like note cards as like an analog, just get something out there, write it down, try to figure something out. And you can always just throw it away because it's just a tiny piece of paper. But and all the best ideas you can write down on like either a note card or a bar napkin. It's like that's how you start a great project. Okay. Am I still rushing? Still have another minute. This one? So today we're going to talk about like what was module 1 about, and then the question, then we're trying to build a question that tests either a piece of that or kind of combines some ideas of module 1. Kind of understand like the general goal. So first step is identifying what were we trying to demonstrate, like what were we trying to learn in module 1. And then next step is how can I demonstrate that I learned it. Cool? So first step is just maybe you can jot down like ideas on one side and then be a question on the other. So what are some topics, like what came up in module 1 that made it like, this is dynamics, this is what you need to know for this first module. Yeah. You can answer. You want to like throw something out there? Which one?
Free body diagram.
Yeah, you got to have a free body diagram, right? Like that's. I'll put a little star. We got to have free body diagrams, right? FBDs. Yeah. Newton's second law. Okay. What were we using? What was special about like Newton's second law? Because I feel like you've seen it before, right? Like what did we use Newton's second law that was maybe a little different from other classes? Yeah.
We derive equations of velocity and motion from them.
Yeah, so we were trying to figure out like position and velocity based on Newton's second law. So the general process to like give you the vocab of like is how to wow your interviewer. It's like I was setting up differential equations using Newton's second law to model forces and acceleration, right? Like now you're really like wowing the engineers and other technicians and stuff. So Newton's second law to set up differential equations. To me, I think that step is the most important part. Some people like get super into like differential equations of like you can spend a whole semester just exploring like all the details of how you solve them and different ways of solving them, and yeah, all sorts of stuff. But I think if like this class in particular is like you need to be able to set them up in order to solve them. And so even if all you can do is like set up, here are my forces, they're all equal to MA, you could just announce to the world of like, hey, I found a differential equation that's unsolvable, and then immediately you'll have like 10 like computational like nerds that are like, oh, we can solve it, we know how to solve this. So like for the engineers, it's like identify forces, identify motion, what are constraints. I think that's the most important part. So that's what we're gonna do. Sorry, I do get a bigger say than a lot of people in the class. Cool. Let me check in, see what other things are coming up. Kinematics, yeah. What about kinematics? What we're doing with those? So, we're kind of like talking about it as a topic. Yeah. Okay. Yeah. Yeah, so setting up like what the definitions for them. Yeah. Graphing, yeah, it's like graphing motion, comparing. Okay, yeah, yeah. Yeah, those are big. Yes, we use other government course when we test that really on something
I'm still one. I think I'm one credit.
No, I'm still like on track with like on the other side. I'm not even like ahead. I know I.
Okay.
Or at least I think I did.
So you were not studying for your.
Not last night. It was after my RG class. In between my changing formula, and then I was like, I can't go to formula.
It was not that long.
Oh, Reese was there. John is here.
Yeah, Gianna was sitting next to me.
I said, I hate y'all.
You should have. No
I
one.
should have looked up something. It took me 4 hours to copy someone's from a homework.
Where's that bad?
I'm just breaking my hand and start to exercise like this, but
You took philosophy in summer.
I looked at my another gen.
They're easy. You have the money.
What?
You have the money.
Doing it like Connecticut this week.
You still get out of state. Trust, I think when you want to but I'm also thinking of the last one.
Okay, I'm working on it. Pretty good, except for it being
Next is gonna be joining the dots color. Yeah.
search each individual flag and make sure that it's in the right order. So if you want to, so I have three flags.
All right, so I'll throw something up there. You tell me what it means. Because I've seen it come up. A couple of people wrote down kinematics. What is that? What does it mean? How did it help, or was it just sort of like a vocab word that I kept throwing out there? So those are definitely like the kinematic equations. So one example of kinematics is when acceleration is constant, we know position, velocity, and acceleration. Like we have that. So kinematic equations are one example of kinematics. But it wasn't always the case. Like we dealt with drag, we dealt with springs, with damping. We had all these different cases where we still had to consider kinematics. What was kinematics in those cases? The motion? Yeah. Yeah, so kinematics is like a general process of how do I describe motion? So, and I'm going to say, like, instead of describe, I'll say, like, definitions of motion. Something like that. So in order to say, like, this thing moved, first we have to know, well, where was it to begin with? Where did it go afterwards? Which means we need some way of describing its position. Which means we need like a vector, some kind of magnitude and direction. So in our case, we're using vectors to describe position, velocity, and acceleration, right? That was kind of the main thing that we needed. So even those kinematic equations are taking one component of a vector that we're saying that we can, because force is a vector, because acceleration is a vector, we can split it up into two components and then have kinematic equations for each component. Cool. And then Python and plotting came up a couple of times. Python, plotting, not like scheming and plotting, but like graphing and plotting. But what else? Did I miss anybody's ideas? Oh, and then like types of forces. So we looked at like a few different types of forces. We didn't capture like every force ever known. I don't know, depends on how deep into theoretical physics you are. Maybe you think there's only a few fundamental forces and everything else is like derivations of that. But if that's the case, then yes, we covered every force ever known. But I think we just covered a few like engineering kind of forces. What were some examples of what we looked at? Drag, yep. Maybe I need some more room. Oh my God. Drag. Friction. Anything else come up? Drag and friction that covers all your bases. Gravity, yeah, that one keeps coming up, right? Gravity. We looked at near surface gravity where it's constant, but and there's also like the GMM over R squared gravity, but we could get there, but it just didn't feel like it. Is that it? Yep.
Normal force?
Yeah, so reaction forces, so normal force, ooh, if I could spell. So like a normal force is an example of, the general term is like a constraint force, that it's going to be as big or as small as it needs to be so that motion can't happen through that. Like something is stopping motion from happening. And we'll get more into that in module 2, talking about like what are the constraints on motion that we can have, like hinges and sliding and those kind of things. But yeah, normal force is an example of like, it's there. I don't really care. Sometimes I don't really care how big it is. I just know that it's going to be as big as it needs to be, such that whatever, like a lot of times gravity equals normal force because that's just how much force there was. But then other things were like spring force, we had like springs in there, like KX, damping, like B times V. So springs, dampers, things like that. And each of those had like a different kind of effect on motion, right? Like friction is like a constant change in acceleration. It slows you down. It slows you down by a constant amount. Gravity, constant acceleration, always pointing down. Drag, now that's a weird one. It's like proportional to speed squared. So end up with weird like tangent of time or something of your of your speed. And then springs and dampers, now we have like proportional position or velocity, things like that. Did I miss anything? Or other topics that came up? Not that we can think of. We can always try, we can look at some questions, and if a question comes up that's like, that wasn't part of our topics, then we could add a topic. All right, so next step is, what's a question that would help, or maybe I'll leave those up there. So this is our, now we're here at the questions. What's a question? It's not going to demonstrate everything. It's not that we want to have like all of these forces all in one problem, but maybe an example that would show, yes, I understand this. Like, how do I demonstrate knowledge in this module? That's the goal here. So how do we demonstrate some knowledge around these subjects? No? Working? Okay.
I was ready.
Yeah, that's okay.
I don't know.
Yeah, you can put it on. If you want to write it in your own notes, that's okay. Yeah. You're not being graded on the note card. Okay.
Maybe just geometry right thematic equations motion for the following.
Oh, okay. Yeah, like identify like what is the equation of motion.
Yeah, it's sort of on the homework maybe.
Yeah.
Yep.
Yeah.
Oh yeah, it's better.
Spider-Man. Yeah. Okay. Yeah.
Because we had like the 3 different types.
Yeah.
Actually cover the forces. And then we had to second law, acceleration, and
Yep.
the rest of the stuff. And then we had like water, so it kind of covered
Yeah.
something like that.
Yes.
So that was-
Yeah.
Do all of it all at once.
I mean, it's covered.
It does cover all of it. Yeah. Very did it once. Yeah. Yeah. It doesn't have to cover everything, but you could describe it, or like what, or you could write out what it means. There's a lot that gets dropped, but it's connected by so how far is it going to drop?
It's just turning on light from justice is what we do.
My econ homework, my first two questions was that, and then which one's bigger?
That's
My 2000 econ. Yeah. I was like that first. I was like, no way. That was my most yeah. Yeah. No, it is crazy. I was that is how you learn. That's the best way to learn. Yeah. You'll never forget it. Oh, I won't. Because now I'm just gonna feel that. You love that. Oh, yeah. I might just be using it more because, like, I might be but we use it for yeah. So, yeah, I kind of just figure out this line first because it's so late next year. But no, I think yeah, that's nice. It's just I don't mind. I like Samsung for actually trying it. I'll just
yeah.
So I sent the email to you last night. I was very late, so but I was trying to access the Jupyter notebook to get everything submitted.
Oh, okay.
I couldn't open the Jupyter to every time I opened it, it would time out and then
Oh, okay. That's okay. Really? Yeah. I don't know why it can do it, but that's okay if you want to like submit it. Or you can submit what you have and then just add it.
Is that fine?
That's fine. Yeah.
So should I ask the question to show you what's going on with Jupyter and then
We can try, but so far it's just been, I don't know, I haven't been able to find like a rhyme or reason to it. Like it's not like if I use a different browser it worked. I don't know.
I didn't know if it was something because like I opened it like 12 or 2 or whatever.
Yeah.
So
It should be okay. Yeah, but that's okay.
I spent like half an hour,
So like one thing that came up, one example was kind of like thinking about something sliding down a ramp. We looked at like skiers on a ramp or like on a hill. But what kind of forces would we see on like a block on a ramp? Or think about like a cardboard box that's like you want to deliver it down the ramp somewhere. Normal force, yep. Where does the normal force point? Yeah, like normal, yeah. And then what else? So far we have acceleration that way, ma equals n. So what other force?
Friction up the ramp.
Oh, friction. Want to add some friction? So we'll say like mu n. That's a weird n, but something like that. And then drag. We want to add drag too. Okay. Force of drag too. And then gravity. And gravity will be like straight down, right? I'm trying to draw it straight down. I don't like that. So what would be like a question? So we have like a free body diagram, and then we could even draw like a kinetic diagram, right? Because we have that normal force that's preventing motion, it's constraining motion, like it has to stay on the ramp. So MA has to be down the ramp. I mean, it could be up the ramp. There's no constraint saying that it can't be, but so then what kind of question could we ask there? Yep.
You could maybe ask what friction constant is required to stop the car before it falls off the ramp.
Oh, could we stop? So if we had friction, could we stop it?
Maybe given like a constant initial velocity.
If we have a constant initial velocity. So like MA equals negative mu n. Well, we can say like mu mg cosine theta. If this is like theta. I know I used alpha last time, but so is there any way that acceleration is going to change here? Because we have a mu, an m, a g, a theta. All those are constant. So we don't have anything, at least according to this, like if it's moving, it's not going to stop moving. At least from this first like thing, right? From first. So what would cause it to stop? Do blocks always slide off of ramps? Or do they sometimes stop? In the movies they stop. Like sliding down, but at the last second, stop. Save the girl. Or the boy, I don't know, depends. Tomb Raider versus Mission Impossible. I don't know. I don't have an answer for it right now, but yeah, so we could, I mean, you could ask, like, all right, so here's like our acceleration, when's it gonna stop? But at least from this equation, it's like a trick question. It's like, well, it's not gonna stop, it's just gonna fall off the ramp at this speed, like depending on how long it was sliding. So we could do something like that. Or we could just say, like, set up what is the equation, like how fast is this block gonna slide? Something like that. Sorry, yeah.
Could you add like motions to static and motion to show it's stopping moving?
To show that it's stopping. Yeah, so I think how would you do it? we would need like a mu static. We would need to solve for when we would have to figure out this question first. Oh, I'm blocking it with my chat box. Chatty Cappy. But we would have to like answer this question first of like when is this going to be satisfied such that, and here like it's not a function of velocity, right? Like it's a constant, like it's based on the angle. It's one way of measuring like coefficient of friction. It's like, have you ever seen that experiment where you keep increasing the angle of a ramp and then when it starts to slide, all right, now calculate coefficient of friction. So you're calculating that static, that mu static. You're not calculating the dynamic friction, different value. All right, so a few possibilities there. Another thing came up was like swimming came up a couple of times. Can I draw a swimmer? I don't know. Let's do this. Not a great swimmer, but not bad. Like, what are the forces acting on you while swimming? Yeah. Okay, yeah, we could talk about buoyancy here. That one's new. So we do have like some kind of buoyancy force. Yeah.
Drag as you're like pushing through the water.
Okay. So which way do we want to put drag?
Like acting against it, so like coming towards.
Towards us, okay. And then, is that it? So we're like floating up and like drifting backwards? Or something else? Gravity. Okay, so we're not continuously floating up. We've got like gravity keeping us in the water. What pushes us forward? Your hands. Okay. But that's just, this doesn't push me.
Is it friction?
Is it friction? But we're not touching any. I mean, we're touching the water, but we're not. Like if I had my feet on the ground, I could say like, yes, I'm pushing myself forward through the water, and there's drag preventing me. But here, I'm doing this. Somehow, I'm moving forward.
Would it be some kind of like normal force because you're pushing against the water and then the water's pushing against you?
Okay.
So you're like pushing forward and pushing back against it?
Yeah. So normal forces. I like you're thinking about it the right way. Of like I'm using some kind of push to get me forward and that stuff backwards. Usually like normal forces are considered like solid, like something push against a wall rather than like kind of flying through fluid. But drag is kind of the same thing, right? Like drag, we're pushing through drag. Sorry, yeah. Oh, drag? That drag is also pushing us forward?
Would be like kind of reaction force between like parts of your body that are, like sort of interacting with the water.
I guess you could think of it as like similar, I think similar ideas of like if I'm pushing this way, there's pressure from the water pushing on me. So I create pressure, water creates pressure. Is that what you were thinking too? Like some kind of use motion, create pressure, low pressure up top, high pressure behind, go forward.
That's sort of what I was thinking too. Like you're pulling water from in front of you, behind you, wouldn't something have to go forward to fill that space so that it worked too?
So vacuum, like
Yeah.
shrimp sort of activity. Have you ever seen like shrimps in slow motion? Oh man, definitely look that up on YouTube. They move their body so fast, it creates like a tiny vapor bubble, and then that collapses instantly. So if you're underwater and shrimp are nearby, you hear like all this like clicking sounds because they're vaporizing water, and then it collapses, and they can use that to like knock out enemies and like stuff like fish and eat the fish. All right, but anyway, so what we're kind of describing is like drag is holding us back, but drag is also pushing us forward. The drag of your hand through the water, like the faster you move your hand, the more drag force is like pushing you forward. Kinda, because we're saying like we gotta push stuff backwards to make us go forward. So we have like force, drag, body. The body is slowing us down, but the hands are actually like say like hand, force to drag feet, force to drag hands, something like that. So we need drag. We actually need the drag to overcome the drag, to like get us forward. Weird. What else did we see? And there, like maybe this one would be more of like identifying like what are the forces, like how do we get forward motion, something like that in this kind of problem. Unless there's a different question about it. Did I miss anything? No? What else do we have? Oh, yeah, like springs. So I think there is this idea of like, we have a bowling ball. And drop it. So drop the bowling ball, something like that. What would that look like? Like where do we start with that kind of thing? Like, and this could be like maybe not like a cartoonishly large spring, like you drop a bowling ball on a bed. Everything's a spring. Like this desk is a spring. If you apply force to it, it bends and then it releases. So it's storing energy. The floor is a spring. It's just a lot of times it breaks. Like if I drop a bowling ball on the floor, it has some spring force, but it also has some like just shattering stuff. So it could be like a bed or a trampoline or something. What would this look like? Is it one free body diagram to rule them all? Like one thing that describes this whole problem? No? Why not?
Well, when it's on the ground, there's different forces acting on it when it's in the air.
There's different forces, right? Like up at first, like from, we'll say from like 0 to 1, it's just mg. The thing's gonna fall from 0 to 1. And then what does it look like from, and we'll say like maybe it gets down to here. What does it look like as it's going from like 1 to 2? What is the free body diagram now? Same thing?
From 1 to 2.
Yeah, so like 1 to 2 is like it hits the spring, and then at least that's how in my head, I immediately kind of split it up into multiple problems. wise. I've been doing it a lot longer than 3 weeks.
Like we have the force barely pull down and then like the spring force pushing that on so people properly.
Yeah. What is that spring force? At least for a linear spring. What is that one?
Yeah.
Like kx, like however far into the spring it gets, right? So there we could ask some kind of question of like, how far is it gonna, like what's the max deflection of this spring or something, or how big does the spring need to be so that it doesn't actually hit the ground, it actually like comes to a stop before it hits the ground, something like that. What else? And how much time do we have? Just a couple minutes. Did I miss anybody's ideas? I know I didn't capture everything, but how is this for a start for quiz 1? Do you want to look at anything different? More involved or less involved? Let's like crank our like how much work we feel like doing. Ramp it up or like scale it back. Let's do like thumbs up with like give me more, or stop. Like thumbs down is just like stop. Don't add any more complication. Stop. Stopping. All right. So this is about the comfort level that we're at so far. It's okay. The goal is like demonstrate that we like understand this module, not to say, let me take on something even harder than I've ever tried in this class. So that's what we're trying to build here. And that's why I do it together, because a lot of times to me, stuff looks the same, but I've been doing it for 20 years, and things that look the same to me look completely different to people that are like just coming to the field. So, and it's more fun to do it together. So we got like sliding, swimming, blocks, or like bowling balls dropping. What do we feel like tackling for next week? This is due like Monday. Goal is like half an hour. That take half an hour out of your day, and hopefully it takes about 10 minutes to do the problem, and then 5 minutes of troubleshooting and record, like all the normal stuff that crops up when you're trying to do work. What do we think? Blocks and sliding, or a swimming problem, or doesn't have to be a bowling ball, could be blocks and sliding. Yeah.
Like a good question could be like something that's shot in the air.
Okay.
With this horizontal velocity from this height.
Okay. So more of like a projectile motion. Yeah.
Something that we could like plot into.
Oh, do you want to like plot something?
Well, I'm saying
Or hand? No. I saw some no's. What? No plotting? No plotting.
Something that we can visualize.
Okay.
Say like swimming or spring force.
Okay. So maybe more like something where, do you want like constant force? Is the goal like constant force? Is that what we're like sort of talking about? We want force to be constant, so we're not dealing with differential equations. We just have like quadratic solutions to differential equations, something like that. Okay, so maybe like either block sliding or rolling. Do you want to deal with rolling or no? Sliding? Sliding's better? Okay. Rolling we'll get to. It's a work in progress, right? We'll get there next time. All right, cool. So maybe we'll do something like something sliding, and we want to take into account maybe friction, maybe drag, or maybe say drag is 0, something like that.